Hello everyone, this is a little project I've designed, and basically it's from a challenge made by Richard. Let me just get his YouTube. Here we go.
Okay, I said challenge. So, Jet and myself both thought that some of you guys out there might like to have a go at this. The challenge is the smallest signal injector, audio signal injector, you can build. Some rules: it has to have a switch or some mechanism by which you press the button to inject the signal, and it has to be battery powered, or at least portable. But I can only think of battery being the way you want to do that, unless you have a little solar panel or something. Hey, I'll leave it to you, but it has to be portable. Yeah, self-powered.
Okay, so I'll just find another bit that he just said as well. Right, and this is the other bit.
The only stipulation is it must be possible to assemble by hand.
Okay. To assemble by hand, I always tend. Well, my eyesight is shit. I'm going, my glasses are ending up like the bottoms of bottles. So I usually go for the 2012, which are the 0805. So I usually go for this size here. So hang on. Let me get my hand. Yeah, I can point better with this. Right, yeah, I usually go for the 0805. All my resistors, capacitors and stuff, LEDs, I always use this size. So the imperial version is 0805 and the metric version is 2012. So that's the smallest I'm going to use. I find them easy to assemble those by hand, although I use a hot plate anyways. But anyway, so I just wanted to just mention that. So this is one of the versions, making one of the versions, and it's powered by a nuclear rod at the end here. You can see that. Let me just I'll get rid of my hand for a moment. Yeah, so if I pick that, basically we just stick this. Oh, not that. What have I done? That one there. So basically that there is how it's powered. It's powered by this nuclear fusion, cold fusion rod, and you just stick that in there and off it goes. But I've added a button anyways. So the idea was you take this out when you don't want to use it and you stick it in when you want to use it. But anyways, that's what I want to sort of tell you about is this power supply that I'm using. So let me get that. Yes, here we are. This is the battery that I will be using. Says 3.6. Now then, it says CR425. Now the way this works, I'll just get the data sheet for this. But basically, you buy them in pack. This is the charger, and you get two batteries. And you can see there. So I think I've got another picture. There you go. So I just bought two of these batteries and a charger, and you just stick these in the end, and on your USB it charges up. I will say though that it takes hours to charge them up. These are tiny batteries, and you cannot push current into them. You have to be gentle when you to charge these up. You've got to be sort of gentle, and you just sort of trickle the current in there to charge them up. So basically, what I do is I'll stick one in there and just leave it overnight. And I mean that's how long it takes to charge one up fully, basically. So I've also got a date sheet. Now it's hard to find a date sheet for these, but if we look at, say, this one, have I got that open already? Right, no. Right, so Yes. So when it says 425, what it's saying there is it's a bit like the normal button cells. You've got 4 mil. It says 42.2 max, but it's referring to 4 mil diameter. So that's how small they are, 4 mil 4 mil diameter. And then you've got an overall length, which is year 25 there. So these are a bit longer and they last a bit longer. And this one is a bit thicker, but I don't know why they've put these other two names here, because that isn't what they are. Although looking at the packet, it looks like they will take these other ones. I reckon they should have just put a black mark on that one there to say that it's the 425. Anyway, so yeah, I'll just get one and show you it on the camera. Right, yeah, so here it is. It's tiny. Hang on, let's see if I can get some focus on that. There we go, that's better. So you can see how tiny it is. If you use this as a reference for size, this is the battery, and it's 3.6 volts is this. I had to check that. Now, there's another thing I need to remember to say. Right, there's two versions, and they're both called CR425. That's what they're both called, but there are totally different batteries. The ones I have, which are 3.6 volts, they are rechargeable. And there's some others that look exactly the same, have the same name, that are not rechargeable, and they only give 2.8 volts. So for my project it has to be the rechargeable ones, because I need the 3.6 volts. One of my devices will not work off a non-rechargeable one because of the voltage difference. So anyway, so now you know how tiny they are. Just give me a minute. There. Hopefully that will give you the sort of scale of this. Now what I'm going to do is I'm going to start on the other version first. So let me just set that up. Right, so this is pretty much the version that Richard originally did. The only difference is I've used what components I had in my bucket, and so these just need to be any general NPN type transistor. Now the resistors, well, I've done these as exact pairs, so it should be an exact square wave. So it should be a 50% duty cycle or period, whichever way you want to call it. And depending on the resistors and capacitors you have here, that will depend on the frequency you have. Now, with all projects I do using a PCB, for those, if there's an option you can add, I will add it. You don't have to have it. So in my circuit I've added the LED. This needs to be quite a high value, which means that LED is going to be pretty bleak. You can just sort of see it just to sort of check that the battery's still charged and alive and working. But I've added that option, and the reason this is quite a high value is because the battery I'm using, of course, is this little CR425, and you saw how small it was, so it won't have a lot of milliamp hours. So I want to reduce the current, basically, so I've put a large resistor here so the LED doesn't draw a lot of current, and I've got quite high values. Really, maybe I should multiply these by 10, maybe would be better, and that would make this battery last a bit longer. But anyway, I just did it for the sake of it. And also I've added an option to stick a resistor in here also, You can either just bridge this connection, or you can put a resistor in. Maybe you want a higher value here, but this one is just the current limiter. You know, you're probing around with a probe, you never know what you're going to touch, so you might want to limit the current that comes up the probe. Or even going out of the probe. Yes, because I've also put a ground on. Let's have a look at the actual thing. So let's have a look at the actual PCB. Just minimize that one. And so, yeah, where was I? Oh, I also forgot to mention, I've put the switch on the negative side of the battery because it's just made it easy. Because the battery's negative is on the pin and the positive is on the actual case. So I just put the switch on the negative side because it made it easy just in creating a slimmer PCB. Oh, and the other thing about the PCB is I've only made it 0.8 millimeters thick. So let's have a look at the 3D view. I'll just go like that. So here's my 3D view. This is of the simple one. You carry it really thin. The only thing that makes it any thicker is because of where the battery is, the size of the battery, and the way I've made it fit. What I've done is I've put some wires through and sort of made it this. I'm going to make this out of some solid copper wire, not too thick, because I want to make it a bit sort of springy. So when you push and pull on this battery, you can just pull the battery out, and then you can just push it in, and it just fits nice and snug between these wires on those connectors there. And then we've got the switch. I've got the option for the the option for the ground is because, well, I don't do amplifiers. I wouldn't be using it as an analog signal, well, to trace signals through an analog amplifier. Most of my work is microcontrollers, and the thing I would probably use it for is maybe switching the state of a flip gate, a gate or something on a microcontroller, you know, or something that an input on a microcontroller. I might want to switch it on and off, and so we've got an option of a ground, so we can put a common ground on, and then I can just probe some pins, and I can switch them on and off at whatever frequency I've set by the resistors. So that's my first version, which is the simple version. Now, the reason I've gone for the rechargeable ones is because the second version, let's just I'll set up the second version. Right, so this is my second version, and it's the one I wanted to do. Like I was saying before, the thing that I would use it for would be for sort of logic gates on a microcontroller or circuit or something like that, where I would want to switch a pin high and low at, say, a certain frequency, and I could see what was going on down the line, in which case I would need the ground attached. Whereas with the audio side, you just need to just stick it on anything that you want a noise on, basically. So so like I said, give it an option to put an LED on there, emit it. If we leave the LED off, it will increase the lifetime of the battery that's plugged in here. Now this is the reason why I wanted the CR425 rechargeable. And it must be the rechargeable version because that's the one that gives the 3.6 volts. The other one will only give 2.8 if it's not a rechargeable one. I need to emphasize that because this will not work with a non-rechargeable battery. The reason being is I've used a I've lost count. 555 timer. But wait, I say, everybody knows that 555 timers usually need 5 volts, and that's correct. Any random 55, yeah, the minimum is usually 5 volts, and that's what you need to power them. But there are some low voltage 555 timers, and that is the 7555 timers. The ones I've got are the ICM 755 timer, and these will work down to 3 volts. So anything lower than 3 volts, you'll get stupid results out of the output. So as long as it's got 3 volt, at least 3 volts, it should work. And so that's why I've used the ICM 7555 timer. It works at 3 volts at low voltage, and so if our battery is giving us 3.6, that means that we have a working thing. And the reason I want to use a 555 timer is because I want a really crisp square wave. For the sort of things that I want to do, I want a really nice crisp square wave, because as I was saying, I would use it with microcontrollers and logic gates and such things. So with the 2 transistor version, you may end up with a bit of a slope as it goes on and drops off, because you're working on the charge and discharge of capacitors, whereas a 555 timer has circuitry built inside to give you the crisp on and off of a square wave. And so this is the version I would build for my type of work, which is to do with microcontrollers and not audio amplifiers. Although it will work on audio amplifier, and you'll get a nice crisp noise out of it. And the way I've set it up is basically this capacitor. This one will set your frequency. If we sort of go, well, it could be half this. I don't know. I always get the values mixed up, but I reckon something like this. I'm using like a 6.8 nanofarad to try and get 1 kilohertz, but I ended up getting 50 hertz. I don't know. I just pick stuff. At the moment, I've just picked stuff out of the box that I had and something close, basically. So, these are not exact values. You can mess around with these values to get your different frequencies. Well, people who know a 555 timer will obviously know that these 2 resistors and this capacitor sets your frequency. So, yeah, that's all there is in there. I've added a decoupling capacitor here as well, and I put the optional capacitor on here, and I've put the optional current limiting resistor, and of course the DC filter capacitor. So yes, so that is my more well, I wouldn't say it was complex. It's simpler, but like I say, I don't think people have used it with a 5.5 timer, because I don't think they realise you can get some low voltage versions. If you're using 5 volts, then any 5.5 timer would be okay. So let's have a look at that one then. So if we go to our PCB, I'll just minimise that. Yep. That's my PCB. Everything just works in a straight line. The one thing that sets the width is this IC. Like I say, I'm using the size of. Hang on, where? Click on something. There we go. This is the size, the general size. The smallest I tend to hand solder. If you go smaller, then well, it's magnifying glass out, telescope. And of course the width is still the same. It's set by this the way I've created the battery holder. If we have a look, it's pretty much exactly the same as the other one. Everything's in a straight line. We've got the button, we've got ground if you should need it, and like I say, the battery fits the same way, and basically that's what is set in the width of the PCB. What I've done is I've made this just shy of 8mm. From edge to edge is 8mm. So if you want to stick it down a pen case, you need one with an internal diameter of 8mm. That'll fit inside. Okay, so that is my preferred version, because it's what I'll be using it for, logic. So what I'm going to do is I'm just I'll show you my works of art. Well, yeah. Before I always send off for a PCB, right? So one thing you should always check as well is, once you've done a PCB, is one thing I always do and never forget to do is run a check and just make sure you get the green lights. I've got one warning: track has unconnected end. Oh right, I know what that is. That is this one here. Look. All I've done is put a thick track there to strengthen the joint to thing, but this end here is not soldered to, it's not connected to anything, it just goes to nothing. So basically what I can do is I'll just exclude that violation, and now we don't have it, so I'll just run the check again and we get the totally green lights. Okay, should always do that before you send a PCB off. And I've done the 3D. Oh right, yes, yeah. Well, that's what I was saying. Sorry. Yes. So once I've done a PCB like this, well, when I'm designing a PCB, so when we're at actually this stage, I do it at this stage. Once we've designed our circuit, what I will do is I'll rummage around my box of bits and pieces and see what I've got. I had to obviously order this because it's a special thing, but then I just pick out what bits I've got, and I will knock up. Although these are all surface mount devices, when I always test the circuit out, and I just use through-hole devices to check, make sure it works. We want to make sure it works before we actually send off a PCB. So I will show you my works of art. One moment. Yes, so here's my works of art. This one, hang on, let's get rid of them leads. There we go. Right, yeah, this one. this is the hang on, where are we? There we go. Let's just see if we can get that into sort of like a focus. There we go. So, yeah, this is my work of art for the 2 NPN transistor version. My diode. This diode's a bit on the big side. It takes too much current. You probably won't be able to see it light up because of obviously my batteries. And then my battery just goes in this bit here. Where are we? Have I got it in shot? No. So if I go through there and I just stick that in. Oh, hang on. Yeah. So it sticks in there like that. And then I can test it out. So that should be working. That I don't know if it's flashing. Have I got that? Oh, I don't think I've got the LED plugged in. Is the LED lit now? I don't know. Oh, maybe not. Right. Anyway, so that was that. That's the my prototype for the two NPN, and like I said, and this one, this this is my. Like I say, I have to use the surface mount 555 or 7555. So I put it on one of these little boards, and then just stick the rest wherever it ends up where it needs to go. But yeah, so that is my my work of art for the 555 term version. So since I've made them up, the thing is to test them out. So what I'll do is I'll set up my my multimeter and my oscilloscope, and let's have a look and see what they do. Alright, so I've got this set up. We'll start with the simple one using the this one with the two NPN transistors. Basically all it is two sets of transistors, capacitors and two resistors. That's it. These other bits are the output and the LED. So it's just these. Oh, and there's two resistors on the other side as well. I forgot about them. Yeah, so let's add the battery in here, sort of thing. And I've got my meter connected up as well. I don't know if you can see these. I've got my two little probes connected, and I'll see if we can get this powered up. Yeah, there we go. So we've got 3.79. It's fairly well charged. Like I say, it's 3.6 is what the thing said, the data sheet, and we can see that it's well, I've got the LED. You can't see it, can you? But actually, I'll show you with the other one, because my other one has got one of the surface-mounted LEDs, and basically all we need to know is if there's a little glow inside it, whether that it's working or not. That's all that's there for. It's not to light anything up or anything, but you can see the current dropping slightly as we go on by time, but I reckon this will work down to 1 volt. Now the thing is with these batteries, you shouldn't never leave them running all the time and drain them flat. They're a LiPo battery, and we know that the rule for a LiPo battery, don't overcharge them and don't over discharge them. So we can go down to I think about 3.2 volts, and we can go up to about 4.4 volt charging. So you don't want to drain these fully, otherwise you'll kill them basically. So that's why with this circuit I've tried to keep the resistors high, so we're using a very little current because we want it to last at least an hour, I would have thought. So we can see that the current, the voltage drop is quite slow there as it goes down, and that's with the LED connected. If I disconnect the LED, let me just disconnect that. That should have altered it significantly, I hope, and it should slow down. So the option for the LED, depending how long you want the battery to last, is there. You'll find I forgot to mention this, but if you want to look for one of these batteries, look for LED fishing lure. LED fishing lure. I can't say that word. Lure. You know, they stick them in the little floats that you throw out into water, and they light up so you can see them at night. That's where you find these little batteries. Right, I'll carry on. So let's have a look at the frequency. So what we can do is we can just stick the probe on. Where are we? and we can see that's the sort of signal that you would just stick into. Let me just bring that down a bit. Oh, I can do it here, can I? Yeah, so forgotten how to do this now. Why isn't that working? Is it my mouse? Oh, it's my mouse wheel. There we go. Yeah. So there we go. There we go. There's a signal. So we've got no earth connected, but it will actually put a noise into a circuit if you're just probing it with the battery. So that's what you're sort of getting, and I'm getting about 50 hertz here, sort of thing. So basically that just into it. But if we're using it for a more like for a digital flip-flop thing trigger, we want a nice square wave. So what we would do is we would use the ground. Let me just stick the ground on, so we'd have a common ground. And there we go. So now we actually have a square wave because we've got the ground connected and it's got somewhere to go. So if I just yeah, let's just increase that. Now can you see that we've now got the nice rounded edge on the on the wave? So yeah, this is the sort of is the sort of thing that is okay in linear audio. When you're just sticking a noise in, you're going to get an on-off pulse. But if I want to use it on a digital circuit, I'd want a cleaner square wave than that, actually. If I was going to be switching a microcontroller circuit on and off, it'll work, it's fine. But that's one of the reasons why I went for the 555 timer. So as you can see, we've still got running nicely, and the voltage is dropping. So the battery, I reckon, one of these batteries will last you a fully charged one will last you an hour. Well, actually, it'll last you more than an hour on this one, because, like I say, this can actually go down to, I think, let me just get the data sheet out. Right, as I said, that the transistor circuit will work on the non-rechargeable ones, which is what this data sheet is for. But it's still called the CR425. But if we look down on the data sheet, we can see there that it runs about 2.6 volts. You know, it comes as soon as if you stick the voltmeter on without connecting the battery up, you're going to get over 3 volts. But once you put a load on, and not too much of a load, it will drop to about 2.6, and this is the time in hours. So as long as so there's the load at 6 ohms, so you can do your maths, do your Ohm's law bit, and sort out the current it's drawing there, basically. So with a 6 kilo ohm load, you should get at least 10 hours out of one of these batteries. Sorry, a non-rechargeable battery. Let me just see if I can find. I found it hard to find information on the rechargeable one. Let me just see what I found. Alright, this is the only information I could find on the rechargeable ones. Like I say, well, this one's actually the 5. Although it's got, it says CG there, so I wonder if that's what we should be looking for. CG, I don't know. But you know what it is when you're buying stuff from China. It comes in a package. Someone says we can make them, let's make them and sell them, and they don't tell you who they were made by or where they came from. So anyway, all I can do is work on this source. So you got a maximum voltage of 4.35. Well, like I said, I use this. It's 4.2, I reckon. But and then you got a nominal voltage of 3.8. Well, I reckon about 3.6. and then there'll be a minimum discharge. But you find these in these interactive glasses, smart glasses, and sort of like bracelet things, stylus pens. You know, they come in these little pen things, and that's what they are. So here's the basic charge. So we don't want to be going down below sort of like 3.5 really, but I reckon sort of 3.2 which should be fine for the lithium battery, and like I say, 4.2 charge. So that's your charge line going up here, and you should stop at that, and then your discharge line coming down. You'll measure this actually with these, when they're fully charged, you'll measure maybe 4 volts, and then when you put a load on, they drop to about 3.8, 3.7, and then they'll go down and they'll drop to, well, as soon as we sort of diving off at 3.5, you should be pulling them out and recharging them. Otherwise, if you let them go all the way down, well, it says you can go down to 3, but you know it's going to drop off, and that's but you want to be, you don't want to going any lower than that, otherwise you'll kill them basically. So that's the sort of data sheet. Let's get back to me experiment. Yeah, I've left it running sort of while we've been talking about looking at the data sheet, and why I had it paused, getting it, and so on. So it's been running for quite a little time now, and we're still getting that nice square wave. What else I can do is, what we'll do is I will connect it up to my my PC on the sound input, so we can hear what sort of noise it's making. Just give me a moment for me to set that up. Well, it's a moment for me, but it's not for you. I hate the pause button. Right, so this is my lead plugged into my computer. Let me just turn on auxiliary. You'll hear a bit of a hum, and if you've heard a bit of a hum at the beginning of the video, this is because I had this turned on at the time. So I'm going to turn this on now, and there should be quite a bit of a hum in the background. Maybe, I hope not too much, because I started the video with it on. But if you can hear the usual hum from the thing. So I don't want to mess around with the sound settings. So just a warning: you might, if you're wearing headphones, take them off, or sort of get ready for a bit of a louder than normal noise. I'm going to stick it on the actual probe. This is with the common ground connected. I've connected the common ground. It's basically going through my oscilloscope into my PC through the common ground. It's the grounds are all connected. So you're going to get, we're getting the decent square wave, and so you're going to get a louder noise basically. So one moment, I won't leave it on too long. Right, I think that's enough. Right. What I'll do is, the thing is that we will be using this with just like a pen with the battery on, so it's portable, and you just stick it on. So when we do that, then you're not going to have the ground. So like I say, I've put the ground on for when I'm doing digital stuff. So if we take the ground off, basically what we have, let's just shorten that. That's what we're outputting. I mean, it's going through all the static in the air and what have you, but it still works because we have an oscillating voltage on the capacitor. So I'm just going to connect it again, and you'll notice that the sound is lower this time, but there's still a signal there that you will be able to pick up on your whatever you're probing and testing. Yeah, it's just a small noise, but you can hear it, can't you, there? So alright, so that's it. So that's that one. So what I'll do now is I'll set up my other work of art. Just give me a moment, or well, it'll be soon because I'm just hitting pause here. Right, okay, so I've got my other work of art. You can see it underneath there, what I showed you. I've got my battery connected up, and that's connected to the multimeter, and so we're getting a nice 396, and you can see that the voltage is really steady here. Now I'll tell you why that current is nice and steady. Oh, hang about, something's not connected. Just give me a minute. Oh, I'm on. Alright, I really messed that up. Right, yeah, I had something not connected. I don't know if you can see that the LED is actually lit. I don't know if you're going to actually get my thumb out of the way. Oh, there we go. It's one of those little... oh, it's gone off again. It'll probably come on later. But you can see that it's off now, and you can see the current draw is very little. You can see the voltage is going down fairly slow. So, like I said, the option is for a diode. It will determine that's the thing. The diode here. Hang on, where's my hand? The diode here. That is what takes the current. What I'll do is I'll just try and kick it off again. So I don't know if you can see it light up. Let me try that. There, got it lit there. So can you see the current is dropping now? The voltage is dropping, and that's with the LED lit. So as I say, the current draw from this version with the 555 is what draws the current is the actual diode. So you can have an option to either leave that on or take it off. Let me just get the data sheet for the 555 or the 755 timer, shall I say. I'll just disconnect the diode, and we should see that voltage sort of slow down. There, it's off now, I think. Is it off? Yeah. It should slow down a touch. So, yeah, I'll just get the data sheet. Right, yeah, so the ICM 7555, I don't know how many fives I did, timer, well, that, yeah, hang on, yes, it is, this is a data sheet. So if we look down, so if we look here, can you, extremely low trigger threshold is 20 picoamps. I mean, is that ridiculous? It doesn't draw. It draws nothing. In fact, if it running, this is the ideal chip for this. Hang on, I'm just looking for something else. And like I say, it has a wide operating voltage of 3 to 16 volts. And full automotive temperatures, so you can stick it in an oven if you like. Yeah. The current is now somewhere. I've read it somewhere. Let me just go down somewhere. Maybe it wasn't this data sheet. Where are we? No, I think it was a different data sheet, I think. We were oh, hang on, right. So we got 3 to 6 supply current. Right there, so it's microamps that we're talking about. This is all it takes to run it. It runs on thin air, basically. You know, So anyway, that's what I was trying to show. Well, that's the reason for the data sheet, is to show you how little current the actual thing takes to draw. And as I say, the actual thing that is so once this is running, the actual thing that will take any current will be the diode, and we know diodes run for are really efficient and what have you. Well, without the diode, this chip is even more efficient. So let's attach a probe without the ground on first. So we've got that running, and we're still at 3.786 volts, so it's drawing very little current. And we'll attach the probe as you would by just using the battery just to make some noise on an amplifier circuit. And we'll just take a look. So there we are. So is it without the ground, the common ground, we've got a similar signal, but you can see that it's a lot more stable than the other one with the two transistors. Let's just go down a bit with that there. So we've got a similar, so it's going to be a spiking high low high low high low high low, and we're going to hear a noise. Now let's just add the ground, which is the way, as I was saying, is I would use it for a nice square wave, and using a 5/5 timer, hopefully we're going to get a really nice square wave. So where's ground? I think that's over there on the blue one. Can I get a connection? Yeah, there we go. So the reason I would use this 5/5 timer is for if I was using the digital on a microcontroller, I would want a perfectly square signal, and you can see that because we're using a 5/5 timer, it is. And like I say, with most things there's pros and cons. If you just want noise, 2 transistors will do, and with a few capacitors. Whereas if you want a proper square signal, if you're doing digital digital work on microcontrollers, you know, flip-flops and all that crap, then you would want something like this to put a nice square wave on, and so you get a nice clean on-offs, shall I say. Yes, so that's why I've gone for the 555, and the battery. But the thing is, with this version, it will only work with the rechargeable types of this type of battery. We need above 3 volts for it to actually work, but it'll work for quite a long time. Will that? We will get a good hour's work out of one. Like I say, you just have a few of these batteries, and the way I've designed it, basically, let's go back to my drawing there. So the way I've designed it is basically so that the battery just plugs in and plugs back out again. So you just swap the batteries like that. So you can just stick it in your charger. When it's charged, you just stick it back in, and then you use it. So that's the way I have done this one. And yeah, well, what can I say? So view my super work of art, given a nice clean, crisp square wave. I think I've covered all. I'm just going to pause and have a think and make sure that I, as usual, haven't forgotten anything. Yes, so as I say, just to recap, I gave myself an extra challenge because, well, basically the timer was the thing isn't really a challenge for me, but my challenge was to get it to use one of these batteries, because these are so small and thin, and I think they're really we could really make some nice projects with this battery, and that was what my challenge was, is to I've added onto Richard's challenge that the battery is tiny and easy rechargeable and changeable, and also that I wanted a clean, sharp square wave that can be used on digital microcontroller circuits. So yeah, I hope you enjoyed what I've done so far, and I'll put a link to Richard's challenge and his video on YouTube in the comments below, and I'd hope you enjoyed. So thanks for watching, guys.